Hello everybody, it is time for a big video in astronomy. This video is all about the HR diagram, or more formally called the Hertzsprung-Russell diagram. And man, is this big! This is the plot of astronomy. Okay, maybe not literally, but you won't find an astronomer out there, somebody who hasn't gone into astronomy, like taken an astronomy class, who is unfamiliar with the HR diagram. It is that foundational. In fact, the HR diagram is almost synonymous with understanding the stars. So I'm going to introduce this diagram to you in this video. Take notes, take heed, pay attention. This is going to be something that we deal with from here on out for the rest of the semester pretty much, because it ties together everything that we need to know about the stars, how they're born, how they live, how they die, how their properties connect, all in one succinct, relatively easy to understand graphic. All right, so hopefully I have properly motivated this. Let's go ahead and dive in to the HR diagram. And I want to go ahead and walk you through this. So the HR diagram, more formally called the Hertzsprung-Russell diagram, the two people that came up with this way of looking at the stars. What it's doing is comparing two properties of the stars. It's comparing the temperature of the star to the luminosity of the star. And notice we have spent a lot of time, pretty much a full week worth of class, getting after these properties of stars, the temperature and the luminosity of the star. With the temperature and the luminosity, we can calculate a third thing, their radius. But other than that, these are the primary properties we've gotten. These are the two easily observable properties. We want to compare them. And a great way to compare them is to make a graphic, sort of an XY plot sort of deal, where what we'll do is we'll put on the x-axis temperature. Although we do things a little bit weird, the HR diagram does things a little bit weird here, where it puts the temperatures running backwards. So we put the hottest temperatures over here and the coolest temperatures over here. So this would be our 3000 Kelvin stars, 6000 Kelvin stars, 1000 or 10,000 Kelvin stars, 30,000 Kelvin stars, and we're talking about their surface temperatures, their photospheric temperatures, which we have seen now can be determined in a number of ways. One of those ways was measure the color index. Measure how bright the star is, its B magnitude using the B photometric filter. Measure its absolute magnitude using the visual V filter, and you get the V magnitude. Subtract the two, B magnitude minus V magnitude, you get the color index B minus V, which gives you the temperature. It's a proxy for temperature. Or we could use that spectral classification, take a spectrum of a star and classify it according to, is it an O, B, A, F, G, K, or M type star? And then give it its number rating as well, so you can get a finer gradation between those. So is it a G2 star? Is it a B7 star? Is it an M3 star? That's also temperature. So here on the x-axis, we're going to put temperature where it increases to the left, or we could equivalently put the color index or the spectral class. So notice 30,000 Kelvin surface temperature stars, those are our O stars, all the way to our M stars down here, our coolest stars. Okay, so we're going to plot the temperature on the x-axis. On the y-axis, we're going to plot the luminosity. How bright is the star? Intrinsically, what is this natural brightness? How much energy is it giving off every second? And we saw that luminosity, we can also measure the luminosity using the magnitude system, where we're talking about the absolute magnitude. How truly bright is that star? How bright would that star appear if it were 10 parsecs away from the Earth in the magnitude system? So now all we're going to do is, and this is what Hertzsprung and Russell were really interested in doing, why don't we look at the surface temperatures of the stars versus how bright they are and see if there's any sort of rhyme or reason. See if these properties connect in fundamental ways. So if you go out there and you start and you get, say, a dot here, 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 so-called a scatter plot, where all the stars are just sort of evenly scattered over the x values here, the temperature and luminosity. That would be a scatter plot, which means there'd be no connection between these properties. There's no rhyme or reason. There's no physics behind the luminosity and the temperature of what determines the luminosity and the temperature of the stars. If that ended up being the case, we'd be lost on really determining the properties of the stars, of trying to get a fundamental understanding, because then the stars, their properties would be truly random. That doesn't sound like nature. So what we'll see is these stars are going to fall in preferential regions on this diagram, that there will be connections between their luminosities and their temperatures. And then we're going to use those connections between the luminosities and temperatures to gain access to other properties of the stars, say the radius, the mass, and other things like that. So then we can learn about just the stars themselves. We will also start correlating different regions of the diagrams. Is there a different, why do some stars fall in a certain region? What is causing that about how stars live and die? So on this HR diagram, we're going to play out the entire story of all the properties of the stars and how they connect, how stars are born, how stars live the majority of their life, and then how stars die. That story can be told with this diagram. Let's go ahead and take a look. So if we're going to go ahead and put a star there, I missed a little bit, but what I was trying to do is I was trying to put the sun right here, which would have a surface temperature of about 6,000 Kelvin and have a luminosity of 1 solar luminosity. Just to give you an idea of how we plot things on here. But let's go out there and start looking at stars and see where they fall. You measure the luminosity and temperature of that star over there, that star over there, that star over there, that star over there, that star over there. One of the first things you'd notice is that a bunch of the stars cluster along this diagonal. So you would see stars from down here at the bottom right, so low luminosity, cool temperature, red stars, to high luminosity, hot stars. And they fall along a diagonal. Where else would you see the stars clustering on this HR diagram? Well, oddly, you see this other clustering over here that are cooler stars, but high luminosity stars. They're red stars, and as we're going to see, they're very, very large stars. You could go ahead and use the radius luminosity temperature relationship to figure that out, that they have cool temperatures, but high luminosities. So they got to be large to bump up that luminosity. So you notice that there's a bunch of stars here. And then you'd see this small cluster of stars down here that are very hot stars, but super low luminosity stars because they're going to end up being extremely small. So yes, you have a high surface temperature, but you have a low luminosity, which means that you have to have a really, really, really small star. There's just not a whole lot of star to be shining. So even though it's hot, it can't shine that brightly because it's just not that big. And then finally, you'd notice it's really hard to find these ones. You have to observe a whole lot of stars and you'll only find a couple. But you'll see some stars cluster right up near the top. And this in general, this graphic that I've created here, shows you where stars fall on the HR diagram. It is not a scatter plot. We have very well-defined regions. We have this diagonal that's connecting the temperature to the luminosity. We have this region up here, and we have this region down here, and we have these ones clustered up here. Let's go ahead and start investigating these. And it's over time that we're really going to start building our understanding of the HR diagram. So we have essentially these 4 regions. I'm only going to ask you to be responsible for 3 of them because that's where the vast majority of stars lie. Almost 100% of the stars will fall in one of these first 3 regions I talk about. This diagonal right here that we call the main sequence of stars. So it's including all the spectral classes, O, B, A, F, G, K, and M. So we have our very hot stars and our very cool stars and everything in between. And we can see that as the stars get hotter, as you move left on the diagram, hotter stars are going to naturally be brighter as well. So something's connecting luminosity, energy, and brightness. This is our good old Stefan Boltzmann's law. here on this HR diagram. Why does it appear kind of as a line, even though it would be energy is related to temperature of the fourth? Notice that this is a logarithmic scale. So each one of these gradations, these grid lines, is a factor of 10 different. So you go 1, 10, 100, 1,000 solar luminosities, 10,000 solar luminosities, 100,000 solar luminosities. And then this scale down here is logarithmic as well. All right, so we have our main sequence of stars. Then we have this region over here. We call this the red giant region. Why would we possibly call this the red giant region? Well, let's use the creativity of naming that astronomers are just naturally endowed with and go, what color are these stars? Well, they're cool stars, mostly M's and some K's, so they're red in color. And they're high luminosity, cooler temperature. The radius luminosity temperature relationship would tell me that these stars are giant, 10 to hundreds of times bigger than the sun itself, and they're red. So let's just call this the red giant region of the HR diagram. So we have the main sequence, this diagonal, where most of the stars lie. Now we have the red giant region. And down here, let's get creative. These stars are mostly around the temperatures of the A and F stars, although they get a different classification because they're not technically stars, they're dead stars. But they would appear mostly white in color to the eyeball. So they are also luminosity, low luminosity, so very small luminosity, super high temperature. You can only get that with a very small radius. Thank you, radius luminosity temperature relationship. So these are dwarf stars, and they're white in color. This is the white dwarf region. And then we call these ones that are sitting up here, these would be our supergiants, where the sizes of the stars are absolutely enormous. There's not very many stars that lie up there. Okay, so this is a graphic that I created. I could have just made this up. Where do real stars plot? Hopefully what I showed you is where real stars plot, but let's actually take a look at some real data. Let's take a look at real HR diagrams. So this is an HR diagram from the Hipparcos catalog. The Hipparcos satellite was launched by the European Space Agency quite a while ago, and it went up there and it measured not only the parallax of stars, but it also could, if it knew the parallax, then it could determine the distance. And if it knew the distance, it can measure the apparent brightness and get the absolute brightness, our luminosity, or absolute magnitude. And we were able to measure the color index as well because it had filters in it. So you could build your color index down here, which is a proxy for temperature, which is a proxy for spectral classes. So this satellite could do this, and it measured these properties, the temperature and the luminosity, for 22,000 stars. And these are the results. This is where the stars that it saw. So here we have our main sequence. You see it's not a perfectly straight line. It's got some kinks and wiggles, but it's roughly a diagonal that goes from upper left to lower right, from high luminosity and hot to low luminosity and cool. Sorry, circle it in the right region. Then you have this cluster of red giants right here, and there's this thin tendril that connects them, but there's a clustering up here. So we have our red giants that are in the upper right part of the diagram. And these are high luminosity, cool stars, so they're giant and red. And then down here you can see our white dwarfs. And you can see some of the supergiants scattered about there, but they're kind of hard to see. So we can see in real data all of these regions. And this, I really like this Hipparcos plot because it has on the axes pretty much everything. So here we have the color index, which then we can put the spectral classes up here and the temperatures that relate to the color index. So that takes care of our x-axis. Notice that it gets hotter to the left, but the color index increases to the right. That's what's the easiest to measure at a telescope. And over here we have our luminosity in terms of solar luminosities. And then over here we have it in terms of what we actually measure at the telescope, the absolute magnitude. Remember that smaller numbers, so negative numbers, mean brighter. So here's our brightest ones, our highest luminosity ones, and here's our faintest ones, our lowest luminosity ones. All right. Now, we can do better than this. Right here, this is the best HR diagram I've ever seen. This is from the modern version of the Hipparcos satellite, the Gaia mission, again, a European Space Agency mission, which on this one, it has measured the color index and absolute magnitude for 4 million stars. So if 22,000 stars wasn't enough to convince you that there are these distinct regions, when you compare the temperature to the luminosity, hopefully 4 million will. And again, we can see the axes are a little bit different. The color index goes a little bit further this way. The temperature is a little bit cooler. But we see the same patterns. We see our main sequence, and here the brighter colors map to there are more stars there. With 4 million, you can't just put the individual dots. You got to actually sort of do a density plot. And here's our red giants. And here's our white dwarfs. So you can see a lot of stars now. And you see the same main 3 parts. These are the 3 main parts I would like you to know: the main sequence, the red giants, and the white dwarfs. And since I'd like you to know these, why don't we actually start investigating these? Why don't we start seeing what patterns there are and how many stars belong to each region? Let's start with the main sequence. And then, just because I think it's a little bit easier and you can see everything with this Hipparcos one, I'm going to go back to the Hipparcos HR diagram. But here we have our main sequence of stars. And the main sequence actually has 90% of all stars. So if you were to observe every star in the universe, 90% of them would plot here on the main sequence on an HR diagram. There must be some really strong connection there that's connecting the luminosity to the temperature. And we've seen that with the Stefan Boltzmann's law, especially the astronomer's version of the Stefan Boltzmann's law. So 90% of all stars fall on this diagonal from the hot, high temperature, high luminosity, down to the cool, so low temperature, low luminosity, so top left to bottom right, this diagonal. 90% of all the stars fall on this region of the HR diagram. Since it's 90%, this is why we call it the main sequence. It's the main part of the plot. So we call this diagonal line the main sequence, and it spans all the spectral classes. And really what we're looking at here is we are seeing the stars in the prime of their life. This is where the stars spend the vast majority of their lifetime. For the sun, it's about 10 billion years, where you add up all the other time that the sun is a star, and you get less than a billion-ish years, somewhere in that ballpark. So spending 90% of its life here in the main part. So I want to be very, very clear. Stars do not move along the main sequence as they age. You basically form a star, and it sits there in the same place on the main sequence, because you're having these stars that are in hydrostatic equilibrium that are fusing hydrogen to helium in their cores. And since they're in hydrostatic equilibrium, gravity pulling them in and pressure pushing them out is balanced. Therefore, they have a nice, steady, constant luminosity. They have a nice, steady, constant temperature, which means they have a constant radius. So they sit still for 90% of their life on the main sequence. And since this is where if you're just going to find a star, it's probably in that 90% part of its lifetime. It's going to be somewhere on the main sequence. Now we can see that O stars, we can start differentiating O stars from B stars to A stars along the main sequence. We're starting to see the O's really are the hot, bright ones, and the M's really are the cool, dim ones, faint ones. And now we have the red giants. About 1% of all stars fall up in this region. You might be looking at this and like, that looks like a lot more than 1% of the dots, Dr. Lindsay. Well, problem is, these stars are all really high luminosity, right? Which means that they're the easiest stars to see. It's hard to see faint stars. So we naturally, with just a satellite that's just looking to see what it can see, it most easily sees the brightest ones. So it's going to see and observe more bright ones than the faint ones, which it doesn't even have the capability of seeing. So, and this, it's over representing how many stars are truly here. About 1% of all stars would fall in this red giant region, in the upper right part of the diagram, the cool part and the bright part. Almost as if I want you to be able to recognize that the upper right would be the bright, high luminosity, low temperature. So the stars that are in the red giant region, we call red giant stars. Nailed it. And these ones have low temperature, high luminosity, and they're giants because they're very large in size. Don't believe me? Take some of these luminosity values and these temperature values, use the radius luminosity temperature relationship, and convince yourself. Or see some of the examples that I did in previous videos. And what are these stars really? These are our dying stars. These are the stars that have already spent their time on the main sequence. They fused all the hydrogen in their cores into helium, and now they're going through the death throes. They might go through some new stages of fusion, or they will go through some new stages of fusion. But once they end their time of hydrogen to helium fusion, they are marked for death, and they rapidly go through the stages to die, either as a white dwarf, if you're a low mass star, or in a supernova explosion, if you're a high mass star. We'll get there. Don't worry about memorizing those yet. In fact, that's going to be the core of a lot of the rest of the class, is just understanding the life and death of stars. And that brings us to the bottom left. So now we have this bottom left part. This part is where we have high temperature, low luminosity. So they're incredibly small, about the size of Earth, but they would appear white in color. So they're very, very small. They're dwarfs and they're white in color. We call them the white dwarfs. And they plot here in the bottom left region, low luminosity, high temperature. And really, these aren't stars really at all. To be a star, you have to be fusing hydrogen to helium in your core. These stars aren't doing that. These are the dead remnants of sun-like stars, low mass stars. This is where our sun will end up. It has about another 5 billion years that it's going to live on the main sequence. And then it's going to transition into a red giant, which is not a very stable configuration for a star because hydrostatic equilibrium is out the window at that point. And eventually, we end up exposing just this dead remnant core of unfeasible material that, floating out in outer space, we happen to call a white dwarf. And 9% of the stars are down here. Over time, that fraction will go up. Well, it depends on how many new stars are being born versus how fast stars are dying. And that's what I have for you about the HR diagram. It is a lovely figure. We're going to spend so much time with it. Print it out, put it underneath your pillow, really get to know it. It is pretty amazing the power that this diagram is going to have. If you remember anything from this astronomy course, you should know the HR diagram. All right, thanks, and I'll see you in the next video.